The goal of this video is to introduce you to functions defined by power series. So what we'll need to do is define power series, and these turn out to be series with a variable in them, and then when you substitute real values for the variable you get actual series. So then a natural question is, how do you discover the values of the variable for which the series converges? And this brings up the notion of interval of convergence, radius of convergence. And then we're going to look at the properties that a function defined by a power series can have. We're going to find out that they're differentiable and that you can calculate the derivative by taking the term-by-term derivative of the power series as intuitively nice as possible. So a power series is an expression of this form, and the x is a variable, and the ANs are all real numbers for n equals 0, 1, 2, and so on. So basically, it sort of looks like a polynomial of infinite degree. Looks like you're just starting to write down polynomial terms, and the degree just keeps increasing without bound. So that's sort of an intuitive way to think about power series. And we're also going to notice that it can be thought of as a potential or incipient series, because what happens is when you actually substitute a real number in for x, you get a good old-fashioned series of real numbers. So let's look at an example. Here's a power series. It's got a nice formula and sigma notation, and you could expand it out. And so there's your power series, and you would notice that in this case, a0, the constant coefficient, is 0. The other coefficients all have a pattern. An is 1 over n when n is greater than or equal to 1. So the coefficient in front of x happens to be 1. The coefficient in front of x squared happens to be a half, and so on. So those are your coefficients for your power series. Now if we substitute x equals 1 into this series, we get the harmonic series, which we happen to know diverges. And also, if we substitute the value -1 in for x, the series you get is the opposite of the alternating harmonic series. And the alternating series test tells us that that series converges. So actually, right off the bat, you now have seen a power series for which one substitute, when you substitute one value for x, you get a divergent series. When you substitute another value for x, you get a convergent series. So apparently, a power series can have different behavior depending on what x you choose. So of course you can pick just any x you want and just see what series you get. There's no problem creating a series. The question is, does that series converge or not? You could do a direct comparison on this guy. This guy is going to be term by term smaller than a convergent geometric series. So actually this guy's going to converge. And when you plug in -3, you get this series, which has alternating signs, but boy, the terms don't look like they're going to 0, or at least right off the bat. In fact, you could use a ratio test and find out that this series diverges. Plugging in 0 is going to give you quite a silly series. Quite obviously converges. In fact, if you think about it, plugging in x equals 0 for any power series is going to give you a convergent series. So I guess it's always possible to make a power series converge by choosing x equals 0. Now, in this example, let's try to be more algorithmic about this. Let's not just pick random values of x and see what happens to the series. Let's go about this the other way. Let's figure out once and for all the values of x for which this series converge. So here we have this power series, and we want to decide when it converges. So we would like to apply the ratio test. Now, we need to square away something here. We've already used the notation a1, a2, and so on for the coefficients of the power series, and we're going to keep those separate from the actual terms of the power series itself. So the terms include the powers of x. So we might use capital A's for the terms themselves, and now we're going to apply the ratio test by looking at the limiting value of the ratio of the n+1th term over the nth term. So in this example, we would write that ratio like so. And you'll notice that we can just sort of move things around and notice a lot of cancellation. A lot of the powers of x cancel. The absolute values really can boil right down to the absolute value of x. N over n+1 is positive. And then for the purposes of this limit, absolute value of x is a constant, so that actually slides out of the limit, and the limiting value of n over n plus 1 is 1. So in the end, the ratio test tells us that the limiting value of successive terms in absolute value is actually absolute value of x. Now, if it's greater than 1 or less than 1, this is going to decide whether the series converges or diverges. So that's great, because when absolute value of x is greater than 1, the series diverges. Well, what does that mean? That means when x is greater than 1 or less than negative 1, the power series diverges. When absolute value of x is less than 1, the series converges absolutely. That is to say, when x is between negative 1 and 1, the series converges absolutely. Now, the test is inconclusive when absolute value of x is equal to 1. And what that means is we just don't know what's happening when x equals negative 1 or 1 based on the ratio test. So if we want to understand that case, we've got to check these things individually. And we'll do that now. So we'll substitute x equals 1 into the series, but what we get is the harmonic series. We know that diverges. And if we substitute negative 1 into the series, we get the opposite of the alternating harmonic series, and the alternating series test tells us that converges. We also know it converges conditionally, because if we checked for absolute convergence, we'd get right back to the harmonic series. So that converges conditionally. And we can summarize the behavior of this in terms of convergence by looking at a real axis, and for each x that we could possibly plug in, we're going to paint that point on the axis one of three colors. Red if the series diverges, yellow if it converges conditionally, and green if it converges absolutely. And what we've just discovered is that we need to paint everything between negative 1 and 1 green, because that's the region on which the series converges absolutely. If the absolute value of x is greater than 1, then we'd better paint such points red for divergence. And then we've learned that at x equals 1, the series diverges, and at x equals negative 1, the series converges conditionally. So this tells us exactly where the series converges or diverges. And you should look at this picture, because you're going to see a lot of diagrams that look a lot like this for many series. In fact, let's look at the general theorem. So consider an arbitrary power series. We don't know anything about A0, A1, A2, and so on. They're just real numbers, arbitrary real numbers. Turns out, though, the behavior of the power series in terms of convergence just can't be that exotic. It's got to fit into one of three categories. The power series either converges only when x equals 0. We know it converges when x equals 0, and there's this case where that's the only place it converges. So that's one possibility, sort of a catastrophe where you get divergence almost everywhere. The other end of the spectrum is that the power series converges absolutely for all real x. So no matter what x you pick, the series converges absolutely. That's definitely a different kind of behavior. And then the more interesting case is one that's sort of in between. There exists a positive real number r for which the series converges absolutely when absolute value of x is less than r. The series diverges when absolute value of x is greater than r. And when x equals r or negative r, the series may diverge, it may converge, and if it converges, it might do so absolutely or conditionally. So in other words, all bets are off at x equals r and x equals negative r. So this third case is one we just looked at. So let's think about this in terms of convergence maps. So in the first case, what you're really saying is the series diverges almost everywhere. The only place it converges is when x equals 0. The second case, the other end of the spectrum, that's when everything's painted green because you've got absolute convergence everywhere. And then the third most interesting case is when there's a value of r for which the series converges between negative r and r. It diverges to the left of negative r, to the right of r, and then at the endpoints between these regions, you just don't know. The theorem doesn't really say what could happen. In fact, anything might happen. So these are your three cases. No matter what power series you look at, one of these will apply to the power series. Now there's some language we use for convenience. So in the first case, we would say that the radius of convergence is 0. In the second case, we would say that the radius of convergence is infinity, and that the interval of convergence is negative infinity to infinity, or just the set of real numbers. And then finally, in the last case, we would say that the radius of convergence is r. The interval of convergence is one of 4 possibilities, depending on the convergence properties at the endpoints. And we would also say the open interval of convergence is the open interval from negative r to r. So sometimes you don't really care about the endpoints, and you want to make a point about what happens strictly inside the interval, and so we'll call that the open interval of convergence. So let's look at this example. Let's find the interval of convergence. So we'll notice that when x is not equal to 0, we set up our limit of successive terms, and we get this quantity right here. Lots of cancellation as before, and we take the limiting value and we get 0. What's the lesson? As long as x is not equal to 0, this limit is 0, and that means the series converges, and it doesn't matter what value of x you chose. And therefore, this is the case B from the theorem, the best possible case for convergence. The series converges everywhere. By the way, we already knew it converged at 0, so it was no loss that we decided, we checked this case where x is not equal to 0. By the way, why do we do that? Because look at the formula. There's an x in the denominator, which is a catastrophe if x equals 0. So there you go. Convergence everywhere. How about this series? So once again, we'll check the case when x is not equal to 0, set up the ratio, and easy algebra again. This time, the limiting value is n goes to infinity is actually infinity. This diverges to infinity, which means all these other choices of x besides 0 lead to divergence. So this is the extreme case A in the theorem where the radius of convergence is 0, and only x equals 0 yields a convergent series. Example D. Once again, we shall set up our ratio of terms in absolute value and do some algebra. And this time you'll notice there's an extra power of 2 in the denominator, and the limiting value of n over n plus 1 is 1. So this limit turns out to be absolute value of x over 2. So what does this mean in terms of our convergence map? Well, we get absolute convergence of the series when this limiting value of the ratio is less than 1. But what does that translate into? It translates into the condition the absolute value of x is less than 2. So we're talking about the set of points between negative 2 and 2. Those are the points, those are the arguments you would plug in for x to get an absolutely convergent series. Similarly, if the absolute value of x is greater than 2, you're going to get divergence, and we have to check the individual cases separately. So let's do so. When you plug in x equals 2, you get a series, and actually if you look at the sigma notation, you realize that the series you get is harmonic. It's the harmonic series, and that diverges. That's easy. Let's plug in negative 2. Well, it's almost the same thing, but we can factor out a power of negative 1 to the n, and now our 2 to the n's cancel, and now you get the opposite of the harmonic series, the opposite of the alternating harmonic series, and the alternating series test tells us that converges. It actually converges conditionally, so let's note that detail. And there you go, there's your convergence map. By the way, using the language we set up, we would say that the radius of convergence is 2, and the interval of convergence in this case is the semi-closed interval from negative 2 to 2, including negative 2. The series converges for all values of x in that interval. So here's a big theorem about term-by-term differentiation of power series. So if you have a function defined by a power series, and by the way, what do we mean by this symbol? It means I'm defining f of x to be equal to the value of the series on the right-hand side when that converges. So if you're wondering where f came from, well, this is where f comes from. I'm defining it to be the value of the series. So if you have this function defined by a power series, and also let's suppose that the radius of convergence is positive or infinite, so we have an interesting function to deal with. So we've got this open interval of convergence on which f is defined, and on that open interval of convergence, it turns out that the derivative exists, and the way to take the derivative is to simply take the derivative of each term in the power series using the power rule. And we've seen cases where there are an infinite collection of operations that all seem obvious, and you want to try to do that infinite collection simultaneously, and it gets you in trouble. Well, this theorem is telling you that in this case, the operation is legitimate. In fact, the derivative of f is obtained by simply taking the derivative of each term and reassembling it into a new series. We're not going to prove that. The spirit of it, though, is because the series converges absolutely on the open interval of convergence, that absolute convergence is what saves the day. So f prime of x is given by this power series. And then finally, the radii of convergence for the two series are identical, although convergence might be lost at either endpoint of the interval. So let's look at an example. So here's our power series from earlier, and now we're going to call this function f. So f is the function whose value is given by the right-hand series whenever it converges. And now we're going to take the derivative. And according to the theorem we just stated, we should be able to arrive at that derivative by simply applying the power rule to each of the terms in the original power series. We've already done the hard work to understand when the original series converges, and we're going to notice that the derivative that we obtained is actually a geometric series. We know something about it already. So let's apply what we know about it already and then test drive to see what the theorem says and if it matches up with our knowledge, our previous knowledge. So we know that this series is going to diverge when the absolute value of x is greater than or equal to 1, and it's going to converge otherwise. And so, in fact, you can see that the radius of convergence is in fact the same, which is exactly what the theorem told us was going to happen. And you can also notice that we had convergence at the left-hand endpoint of the original interval of convergence, but when we took the derivative, we actually lost the convergence there. So again, we were warned by the theorem this might happen, and indeed in this example it did. We lost convergence at one endpoint. So now a corollary of this theorem is a statement about term-by-term integration. It stands to reason that if you can take derivatives, if functions are differentiable, you can find their antiderivatives. So what's the only possible way that we can take the antiderivative of a power series? It's got to be in such a way that when we take the derivative, which the original theorem guaranteed, it'll get us back to where we started. In other words, use the anti-power rule, or the power rule in reverse, for each of the terms of the series. So you have here k, constant of integration, a naught x, 1/2 a1 x squared. These are all we're anticipating the power rule. We're just finding the antiderivative of each of those terms and reassembling a series. And just as the previous theorem stated, the radii of convergence has to be the same, because if it stays the same when you take the derivative, it better not change when you take the antiderivative, or you go in a little loop back and forth and you're going to get a contradiction. Now, if you're going backwards, you might gain convergence at an interval because, once again, you lose it going the other direction. So maybe when you find the antiderivative, you pick it back up again. So let's look at our example again. Here's our original function. We're going to find the antiderivative term by term. We've got our k, which is there for any integration, a constant of integration. If you have a particular problem, you can probably figure out what that value has to be for your application. But otherwise, you're just using your usual power rule in reverse to find the antiderivative of each term. Here's our original sets, our map of convergence. And so this time we're just going to let the theorem tell us that the interval of convergence is going to be 1 for this series. We don't have to analyze it. We can use the theorem to tell us that the series will converge absolutely on the interior of the interval from -1 to 1, and exterior to it, it's going to diverge. And now we only have to determine what happens at -1 and 1. So we plug these in separately, and you'll notice in this series, if we write it in sigma notation, that when we plug in 1, we get this series. When we plug in -1, we get this series, which is an alternating series. And if you wanted to check that alternating series for absolute convergence, you'd arrive at the same series on the right here. And that thing looks an awful lot like 1 over n squared. In fact, you could do an easy limit comparison with 1 over n squared, and that reveals that the series converges, which means that the series converges absolutely at each of the endpoints of the interval of convergence. So there you go. Radius of convergence 1, closed interval from -1 to 1 is the interval of convergence. You'll also notice that we did not have convergence at the right-hand endpoint, but after we integrated, we picked it up. Let's end with a warning. These statements are about taking derivatives and antiderivatives. They should only make sense on the open interval of convergence. You can't make sense of, for example, finding a tangent slope at the edge of a domain where you've chopped off the graph. Nevertheless, it is true that the derivative on the left side might well be still represented by the value of the power series on the right side at an endpoint of convergence. You just need more rigor to really justify such calculations. However, that shouldn't stop you from playing around with these equations by plugging in endpoints of intervals of convergence. You can still uncover some really wonderful mathematical truths that way, even though you're not necessarily justified in the most rigorous sense in knowing that it's true. You can still wind up arriving at a true statement and appreciating it. So don't let that stop you from playing around with these power series equations at endpoints of intervals of convergence.